So hierarchical clustering. So this is basically another way to, oops. This is another method inside of k-means. And there's actually quite a lot of advantages and disadvantages or quite a lot of advantages over k-means that's gonna be useful here. So one is that the hierarchy part is going to be really useful. So what this is gonna represent, and this is from the curriculum here, kind of half of it, is it allows us to find clusters within clusters. Essentially, every cluster is a cluster of clusters of two parts. So you can see here, our very first cluster here might be C and B, and then A is kind of that cluster, but then we can see E and F are clustered, and then that D part, and we can see all of these are really clustered together versus all of these clustered together. So this kind of builds up this hierarchy in the sense of saying, oh, what things are really small clusters and building up. And so you can kind of see, so if we can figure out this structure here, that means we can say, hey, if we only want 2 clusters, we can find, oh, these are the 2 clusters going on here. If we want 3 clusters, it likely can be, hey, we can find 1, 2, 3 clusters, right? So you can see how this can be really useful. What's also nice too is that we can actually make these visualizations. So you can see here, this is 2-dimensional data, which obviously relies on the fact that, hey, if we don't have 2-dimensional data, it's gonna be really hard to visualize this. So we actually have this nice thing called a dendrogram. And a dendrogram basically allows us to plot out this extra hierarchy. So this is from the curriculum here, is that this dendrogram on the right here is kind of representing this kind of I would say a clustergram. So the idea here is these are all the different clusters, but these are going to represent the actual groups together. And what's nice about the dendrogram over here is we can visualize this in very high dimensional space, high dimensional separation. So basically is that we can kind of figure out a little bit of how these groups are supposed to put together. We can just choose what n clusters there are. So like I said, if you want 2 clusters, you can say, hey, from this dendrogram or from this part, but you can see in this dendrogram, this would be 2 parts right here. This would be 2 clusters right here. So the way I kind of would picture this is if I took a little let's imagine these are all hanging on a string, like a mobile, right? You guys know what I'm talking about, right? A little mobile stuff kind of spin around in front of little babies or something like that. And I would just go ahead and just cut this part. So I cut this part right here at the very first connection. That would give me 2 clusters. It makes it really easy. Then I just go down further. It's well, what if I want more than 2 clusters? Well, okay, let me go down further. Say, hey, let me cut down the next level, which is this one. And I cut this one. Now we have 1, 2, 3 clusters. And you can see that 1, 2, 3 is this one, D, E, F. And we can see this part. It's well, I really want 4 clusters. Well, I cut down the next one, boom. And you can already see is that when I do that, you can see, hey, there's my 4th cluster. Okay. So you can see how really useful this is. Hey, if I want to know how many clusters are, I want to split them up later on, I can actually do that pretty easily just by looking at the dendrogram. And remember, the dendrogram is nice because you don't have to worry about dimensional. This looks the same. This dendrogram looks the same regardless if it's 2, 3, or 100 dimensions. So this makes it really useful for us to see. And you can already see a little bit of that clustering going through here. So again, dendrograms are going to be really nice to kind of see hey, does my clustering algorithm actually work well? And again, the whole idea is that clusters are more alike. So we start off with the things that are most alike each other, like this, for example, C and B are very closely related. C and B are more closely related, but they're kind of related to A. And you would maybe say, well, D, E, and F are really close together, but all of them together are more closely related than any other points. Okay, and that's the idea of the hierarchy. Okay. Does that make sense to everyone? Okay, so that's kind of what this what's it called? Hierarchical clustering is doing. So let's talk about the different types. So one thing to do is okay, we need to figure out what things are close together. And this is where it comes in some extra complexity. So I don't have a good visual for this because I took this from the curriculum, but imagine all of these circles are not there, right? Clustering together. How do we actually do this? Well, what we do, we basically start with the first, let's say A right here. And we say, okay, which is the closest one to A? Well, closest one to A is going to be this point right here. Let's say that's B, okay? And that's okay, well, these 2 points are closest together. And I actually think, well, we'll just go with this. So we'll just pretend A and B are really close together, okay? And then we would find the next 2 closest points. Well, the next 2 closest points by themselves are E and F, and then I and J, and so on. And essentially we kind of cluster these guys together and say, okay, what's the next distance over? Well, the next distance over is C and B. It's oh, well, this is our first cluster right here. And say, okay, from these points right here, it's okay, these parts are the closest part. So the hard part though, that's gonna be in here is it's like, how do we determine, you say this E and F, which are a single cluster, how do we determine the distance for this D exactly? And that's the part where we say, okay, it depends if we count, like, for example, the closest point. Do we count the furthest point or farthest point, F? Do we count the average between the two? Like, that's how it determines, like, you know, these different types of hierarchical structures. That's going to be the determining factor of like how we combine these together. So that's what we're going to look at next. Okay, so let's go to types. Okay. And then this is one here. I'm going to mention single link. Single link is not even like available in sklearn because it's so bad. Like single link is so bad, like it's not even worth like doing it, but it's important to kind of see how it goes through. So single link, imagine again, these points don't have these like dots around here. Essentially is the links between the two. It's going to be the closest point. So imagine if we already have clusters C and B and E and F and I and J. What we're going to do is say, hey, let's go ahead and look at the closest points. So like, let's say from cluster 1 over here, this cluster, we'll call this cluster 1, cluster 2, and cluster 3. Okay, we say, okay, this point right here, we'll say H and F are the closest ones. Then we have, let's say, C and E. Okay, and so we can see like these are the next closest parts. It's like, well, we just use like, okay, this point is closest to this point over here, and we can combine them. So okay, this is going to be the next group over this side. Note that we're using this exact points. However, if we have, and I'm going to draw off this side over here, this is where some issues, and this is why no one uses single link. So if you instead have data points that are kind of like in this square right here, and you have something like data point, and then say data point, data point, data point, data point, data point, okay? And let's say we first make a connection of like these two. The problem is that these will kind of like end up because it's always gonna be the next closest point, it's always gonna kind of keep going in this direction, making these long snakes, which might not seem like a big deal. However, if we have something like where these points are kind of like over here, where basically it's only going to consider the very closest point every single time. And what happens is that this is not going to be related anymore to the rest of these ones. So it's only looking at the very closest point. So it tends to kind of like reach out a little bit and grab up. So we tend to create these like elongated clusters. And it's kind of reaching out to other points. And then it tends to eat up a lot of points for a cluster. So what will happen is that basically this cluster will end up getting all the points, and this cluster is going to be all hungry where it's only 2 lonely points. So you'll tend to have one very dominant cluster, and it tends to be very long. It tries to snake out. It kind of like pulls out the closest one. So you can see like that might not be really ideal, because we really want it to be the ones that are in a cluster are really should be close together, or sorry, not close together, should be really similar to each other. Okay, and remember, our similar to each other is by distance. Okay, so you can imagine like having like a really long structure like this, where this point really isn't anywhere close to this one. They're not very similar to each other, and you'll tend to have this very dominated cluster. So that's where we say, okay, forget you single link. Let's try a better one. So complete link is more rounded in this case. In this case, it's basically the same thing as single link, saying which is the most closest point, except it says only compare the farthest points. So it says, all right, we have our different clusters, and it says, what is the farthest point from this cluster to this cluster? And then they say from this cluster to this cluster, and it says, all right, we have the farthest point, which of those distances is smallest? So if you imagine, I'm just gonna kind of draw it over here. I always do stuff with my hands and I realize I can just draw. Okay. So if you imagine like you have this cluster right here, let's say this cluster right here, and let's say this cluster right here. So it's gonna take the furthest point, let's say there's 2 points like this. I'm just gonna draw it simple. And let's say I have in this pink here, the farthest point from here to here. That's the farthest one. And then let's say the farthest one to this point right here is going to be like this one to, oh, let's go ahead and do this one to this one. And then the farthest points from these 2 points, and I'll use a different color just to make it really obvious. I'll use blue. From this point to this point right here. And so it's using the farthest points between the 2 clusters. Okay, but it's going to say, okay, which is the closest of these lines now, or what's the smallest line? So, oh, this blue line is going to be closest. So this should be the group right here. Does that make sense? Okay, So we're still using like how far, like which one's the closest to it, but we're determining that from the farthest 2 points from those 2 clusters. Okay. So the idea here is that like the ones that are farthest away, even like they're supposed to be the most different from each other, right? Between the different clusters. But even considering that's like, well, even though you're the most distant from each other, you're still more similar to each other than the other groups. And that's the idea with this line here. Okay. So that's a good, it ends up being a good balance. It tends to create more compact clusters, which is what we want, things that are really similar to each other. However, note that it tends to ignore points that are similar to the actual cluster because you're only considering about very far points. If you happen to have like a, let's see if I can just go ahead, make this really quickly. If I have like a cluster that formed like this, and I have this point right here, and then I have, let's say, this right here on the side, instead of considering this close point, it's going to only look at this thing right here. So what's going to happen is that it's going to tend to look at things that are very dissimilar to it. So this is kind of the opposite extreme where it tends to try to gobble up things. It'll tend to relate things that are not very similar to the rest of the cluster. So if you imagine this cluster has like mostly these points over here, and then there's this lone point over here, it's going to try to combine this point together. I'm trying to give a good example here, but you can kind of see like how this point right here, because it's so far out, if it starts relating to other distances, this is going to start determining how this cluster forms. Does that make sense? Okay, hopefully that wasn't too confusing, but you can kind of see how this distance point is going to be essentially dominating everything else. So you're going to end up getting things that are actually very different from the actual full cluster. Okay, so you can see, all right, complete link, not bad, right? Better than single link. But we kind of compromising some of that similarity. So say, hey, compromise that similarity. Hey, let's try average link, where basically the same idea here, except instead of looking at any individual point, we just essentially average out all the distances from point to point, which probably would be like your natural, if I started here and say, okay, we'll only try the extreme part for this, and oh, that didn't work very well, let's just average them. That's what this point would be, okay? And so does that make sense for average? I don't think I have to kind of go through that whole process, right? Okay, so the last one is probably, I think, the most counterintuitive, but kind of leads from like, going from complete link to average link, is called ward. And so ward is trying to minimize the variance between cluster merges. And essentially, I'm not going to really try to show this too deeply. Here's the actual equation, but essentially what's happening is that it's going to look at the center between the clusters, and then it's going to find the distance from those centers to each cluster center. And what's going to happen essentially, it's essentially an averaging, but it's being a little more careful, where it's not just averaging across the data points itself, it's more like averaging across the cluster size. So you can kind of imagine if I had a, oops, and I'm not going to be rigorous in this case, but you can imagine we have two different clusters like this. It's going to look at, say these are my 2 points. It's going to say, okay, here is my center right here. Here's my center right here. And it's going to say, how far are each of these points from the center? How far are these points from the center? And basically average those 2 points. So the idea here is kind of like an average between the 2 averages. The main idea here is that just know that ward tends to be most well-balanced, best performative. This is the default in sklearn when you do hierarchical structures using ward. Okay. But anyway, I think, it takes some time to kind of go through this part. To be quite frank, it's not super needed to stress out about it by itself. But the idea here is that you're just trying to find that average, that center point of this cluster, and how far they are to every other point, and minimizing that. Okay. So this is kind of like measuring different distances. Okay. Cool. So more or less understandable for these different links and how they can be combined. Just know these links are basically just determining how far a different cluster is from each other. And then based on whatever the smallest distance is, however we define that, depending on what link, then we basically minimize that and combine them. Okay. So check out some code then. Does that seem like a good one? Good old code versus me drawing. All right. So I'm just going to use the iris data set here. And I'm going to show you a little bit how to kind of make these little dendrograms. Unfortunately, sklearn does not have dendrograms available in it, so I have to use SciPy But you can kind of see what's going through. But you can see I can actually make these clusters with sklearn by itself. So you can see I'm importing cluster. This is just data right here. So I'm just using the iris data. I'm only using 70 just to make it a little bit readable. And I'm going to say there's 3 clusters. I'm using linkage ward. Note that this is the default. If I do a little tab here. Oh, well, of course it doesn't work because I have to run this first. There we go. So you can see ward is going to be, where are we at? Linkage ward. So you can see it's going to be the default already. But essentially that's how we're going to link them together. And they say, okay, from this cluster, this is my model right here. Okay, I'm going to go ahead and predict it off of this X data. And that will give us our different clusters. So now what happens is that I actually have it all trained up here. Okay, so this is basically, okay, it's all trained, it's all ready, it's fit on this X. Okay, so to kind of show you a little bit, I wrote this little function right here to basically create a dendrogram. So this is just showing you from this model, we can see the dendrogram of like these hierarchies. And you can see here, these are the 3 going, like the best way to read these things are coming from top bottom. So this is like my first group right here. And if I go down here, if I want 3 groups, I'd split this one, right? And this would be 1 group, 2 groups, 3 groups. You guys see that? Yeah. And so it's easiest to kind of start from the top right here. It's like, okay, I split off that. If you imagine, like I said, like you cut this, right? Like, so, okay, let's go and cut this part. That leaves us to this group right here off to the right, and then these 2 groups, and then split this again because we want 3 clusters. You can see that this is going to be 1 whole group by itself. And this will be 1 whole group by itself. And this will be 1 whole group by itself. Okay, does that make sense? Okay, so note that I also used, let's see here, this guy right here. This one, again, this is using sklearns. I just wanted to show you a little clearer because it's not the best, unfortunately. But I don't know, it's just kind of what it is, unfortunately, to get emphasis to kind of show a little bit. But you can see here is that this makes it a little bit clearer, I think, to see like how closely related they are. This is using the dendrogram like, matrices. So I had to like convert it over to this special thing called ward to make it plottable in this way. Unfortunately, they're not compatible in that way, so I have to do some kind of processing to basically change it over. But you can kind of see here, I think it's a little bit easier. You can see there's definitely a group right here. In this case, it's actually identifying this as 1 whole group by itself. But you can kind of see is that this really should be split up into 2 groups because you can see how different they are from each other. And you can even argue that maybe there's some subgroups within this larger group. Okay, but you can see the roughly structure. Some data sets are going to, like the iris is probably not the best example because there are 2 of the classes are very similar to each other. So I think class 2 and 1 are very similar to each other. So it has a hard time determining these 2 parts. But certain data sets will be really clear where it's like, oh, there's clearly like 1 structure here, 1 structure here, and 1 structure here. So it lets you kind of like ad hoc, instead of you determining ahead of time what cluster it is, you can say, oh, well, I need 3 clusters. So I can go ahead and chop off the parts and I get 3 different clusters. Okay. Does that make sense to people? Cool. Yeah, and of course you guys can check out the, what's it called, the repo and kind of play around with this a little bit and kind of see how it goes through. Honestly, this took me a while to form properly. It wasn't an easy task. So just kind of know that doesn't exist right now. But anyway, so advantages and trade-offs. So one big advantage to this is that we can visualize our clusterings. So versus k-means, we'd have to essentially plot out the points, which means that if it's not 2-dimensional or 3-dimensional, it's really difficult to plot this out. Dendrograms in particular are really useful for us to plot out in high-dimensional space. Also, this hierarchy can give us more context. So we can actually see things that are very similar to each other versus saying, oh, they're different groups. We can actually kind of use this idea as like, oh, well, these are really similar to each other. And therefore they are, they should be considered a group. So we cannot have a hierarchy of like what is the most similar to each other. So because of that, we can actually use this for data sets that are or data sets that have hierarchical relationships. Think things that are already like, you know, a cat is closer to a dog than it is to like an alligator, right? For like taxonomy or something like that. So you can actually use this hierarchy structure if your data set already is hierarchy. So like you can imagine if there's features of like reptiles and mammals and birds and stuff like that, there'll be a certain amount of features. Those features will be grouped together without you saying what is the right, you know, grouping to do. They say, oh, well, these are very similar to each other. But then these are more similar like to each other than other things. So you can, like I said, a dog and a cat, or both mammals, tend to be very similar to each other. They both have fur, whiskers, give live birth, versus something like an alligator, where it's like, oh, you have scales and they don't give live birth. So like they have eggs and everything like that. So you can imagine there's some like features between those two. So it makes it really nice to have that hierarchy in there. Okay. So those are some advantages. So you can already see that it's pretty great compared to k-means. Some disadvantages is that it's expensive to compute. So we've seen like order, like a big O notation. Maybe thumbs up if we've seen big O notation. Okay, maybe thumbs up and maybe sideways, but I don't remember it, but like maybe you've seen it, something like this. So big O notation basically is computer science way of saying how long things like take and how much space things take up. Turns out if you have many, many features, that's what this n represents. If you have many, many features, it can take a long time for them to determine the different groups. And that hopefully makes a lot of sense, is that essentially if you have many, many features, it means you have to measure many different things on the vector space to know how far something is from each other. So again, this can be very, very, what's it called, sensitive, or not sensitive, computationally expensive. So one thing too is really sensitive to noise and outliers. So the problem is that I think this is actually a really great example. I had, where is it? Okay, mean issues here. You can kind of see right here is that Warden agglomerator clustering. You can kind of see is that if there's some extra like noise in here, it doesn't really know how to treat it. Like if it's like, oh, this is kind of like extra noise that really shouldn't be counted. Like there's a point over here. It's going to try to make that into a group. So it doesn't really know how to deal with noise. It's like, no, this is either a classification or nothing else. There are no outliers in hierarchical clustering. Does that make sense? So like there isn't something that's going to be like, oh, that's not part of any group. So that's going to have an issue here, which actually leads really well into the next part, which I don't think we have enough time, so maybe we'll hold this off, but is if there is noise and it's having a hard time doing noise, there's actually some useful algorithms like dbScan. So I'll do a quick just intro before we head out, but dbScan, just to kind of look at it a little bit, is that it's going to identify and kind of, oops, there we go. I'm just going to show you really quickly what this looks like, because we'll do this next time before we do pipelines. This is fun to watch. So basically dbScan does kind of the idea of clustering, but actually looks for noise. So you can see how it's going through, basically just trying to identify the different points and figure out what things belong to each other, and it moves on to the next point. And what's interesting, you can actually adjust how much noise you're allowing it to do. So you can kind of see going through here, it's going through its process. We'll talk about this, what it's doing next time, but you can kind of see this whole process going through. In this case, you can see it identified this being a little noise point by itself, never classified it, which is useful, which is like, okay, like depending how I adjust this, a threshold. But you can see, for example, a pimpled smiley, which I love. So actually I'm gonna go here because it's the same person who wrote it, which is awesome. Pimpled smiley, this is for k-means. You can see there should be like 3 points, but you can see how it's gonna be like, 4 points. But you can kind of see a little bit, it's not gonna do very well performing this like circle, these points right here. And it's gonna have a real hard time with these extra noise points. So when we do dbScan right here, okay, you can kind of see, and this is just visualizing the epsilon, but it'll start basically identifying those points, and it'll start by saying, hey, these or at the end, it'll say, hey, some of these points right here are not fair, like should not be associated with any cluster. And so this is really useful for like finding outliers and stuff, or so your outliers don't affect your clustering algorithms. Think things like financial transactions or something like that too, where like you want to have something like something way out to the side. Noise is actually or outliers are a really important part. We can actually use that to say, hey, that might be fraud. Like this doesn't seem like a normal kind of situation. And you can see here the little process, like for example, it's turning this part's like, oh wait, there's this part. And I think this all depends on exactly how much noise is going through here and what we change this epsilon. But you can see it does a much better job identifying that these are different groups together. And this might be like, depending on like how you adjust this like threshold. But you can see here, all those points that's labeling, those are all noise points. So did a decent job, not perfect, but we could probably adjust that epsilon. So anyway, that's dbScan very quickly, but we'll maybe talk about that next time. For now, hierarchical clustering is a really useful one in this case, where essentially you can kind of use it to help determine what clusters are. without having to know that ahead of time. So this one tends to be, k-means is nice because it's kind of like relatively straightforward, but hierarchical clustering will tend to be more useful. And we saw with these issues right here, you can see they tend to perform better for these groups right here, where k-means has a real hard time determining these kind of interacting counterparts. And you can see here on this part, dbScan. dbScan does a pretty decent job of finding out like what things are noise depending on what threshold you put in. Okay.